Welcome back to the Fast Neutron. This is installment 3 in my ongoing series on the basics of nuclear science and engineering, and it's the second part of a pair of videos on nuclear decay. Today, we're going to be going into the mathematics behind radioactive decay. If you haven't seen the last video, I would highly recommend checking it out. We went over the different common types of nuclear decay and discussed the kinds of isotopes that tend to give off energetic particles through these different modes. While you can certainly pick things up from here, I think the last video should help you gain a little bit of intuition on why some atoms undergo decay. For today's video, we'll start off by introducing the concepts of decay constants and half-lives. These quantities are the building blocks we'll use in constructing equations that describe how populations of radioactive isotopes change over time. After that, we'll talk through the concept of activity, as well as the units we use when talking about activity. From there, we'll do a quick section on branching ratios, which come into play when a single isotope can decay in more than one way. Next, we'll solve some basic decay equations with and without isotopic production to contend with. And then finally, we'll talk through decay chains and do a couple quick examples to show how we can predict the populations of different species of isotopes over time. Here, we'll introduce concepts like the Bateman equations, transient equilibrium, and how the matrix exponential can be used to make our lives easier in these calculations. To motivate our discussion here, it's good to remember the simple fact that different unstable isotopes can and do decay at different rates. If we have a single atom of uranium-235, it's likely to stick around for the better part of a billion years before it decays via alpha emission into thorium-231. For other isotopes, like say chromium-47, you wouldn't have to wait more than a half of a second before you can expect it would have undergone beta plus decay into vanadium-47. And there's a plethora of isotopes that last a much shorter amount of time than that. The rates at which different isotopes decay span many orders of magnitude, 54 orders of magnitude to be exact. And the quantity that underpins these rates is called the decay constant. This constant effectively describes the rate at which a given isotope undergoes decay. We represent decay constants with a lowercase lambda, and decay constants have units of inverse time. For a given isotope, the decay constant is defined as the reciprocal of the isotope's mean lifetime, which we represent with the Greek letter tau. So an isotope with an expected lifetime of 10 seconds will have a decay constant of 0.1 inverse seconds. And for every second that passes, the isotope will have a roughly 1 in 10 chance to undergo decay. Now, a crucial point of note here is that decay constants are in fact constant. They don't change with time. Atoms have no memory of their state, so the probability that they undergo decay doesn't change as time passes. Let's say our atom with a 1 in 10 chance to decay each second has, by some miracle, survived for a whole hour without decaying. While the probability that this atom lasted that long is extremely slim, it still has a 1 in 10 chance to decay in the coming second. Nuclear decay is a purely stochastic process. You can think of unstable isotopes as constantly rolling a many-sided die to determine whether or not they will decay. If you're familiar with a little bit of statistics, it's probably already dawned on you that the rules we've laid out here for radioactive decay describe a Poisson process. As such, for a large collection of isotopes, the Poisson distribution can be used to model the number of decay events which can be expected to occur as a function of time. As is the case with any Poisson process, if the number of participants in the process grows large enough, we can use exponential decay to model how the participants change state over time. So if we have a collection of an isotope with an initial population of n sub naught, the population n of t evolves over time through the following exponential decay relationship. This is the solution for the following differential equation, which governs how isotope populations change over time due to decay. dn over dt equals negative lambda n of t. Now, let's talk about the concept of a half-life, which is definitely more widely known than that of decay constants. Put simply, an isotope's half-life is the amount of time it's expected to take for a large collection of that isotope to fall in population to half of its original value. We represent half-life with the symbol t sub 1/2. The half-life is directly related to the decay constant through the following relationship, where the half-life is equal to the natural logarithm of 2 divided by the decay constant. To give a little bit of visual intuition here, let's draw a quick plot. On the y-axis, we'll have the relative population of a sample of an unstable isotope. On the x-axis, we'll have time, and we'll put this in terms of the decay constant. Now from earlier, we know that the mean lifetime is equal to 1 over the decay constant, so we can write the x-axis labels in terms of tau. As we plot the curve that describes the population over time, we get the familiar shape of exponential decay. Now the first thing I want to make clear here is that the mean life of an isotope is not equal to its half-life. At time 1 tau, the population hasn't reduced by a factor of 2, but rather by a factor of e, as tau is the mean of this exponential distribution. At t equals 2 tau, the population has reduced by a factor of e squared, and at t equals 3 tau, a factor of e cubed. The half-life is analogous to the median of this distribution. So after one half-life, we're left with half of the original population. After 2 half-lives, just a quarter remains, and after 3 half-lives, just 1/8. A good rule of thumb to remember is that for every 10 half-lives that pass, the population of a radioactive isotope will decrease by a factor of 1,000. For small releases of radioactivity during, say, an experiment in a lab, this rule of thumb can be used to quickly come up with an estimate for when the affected area will be safe to clean. Now, let's move on from decay constants and half-lives and talk about activity. Put simply, activity is the rate at which radioactive decays are happening at some point in time. We can conceptualize this as follows. Anytime the population of an isotope changes, a radioactive decay must have occurred. So for a collection of isotopes undergoing decay, activity, the rate at which the decays are occurring, is equal to the rate at which the population of isotopes is changing. So we can get an expression for activity as follows. dN dt will be equal to negative lambda times n of t. Therefore, activity is just lambda times n of t. The faster the population decreases, the higher activity will be. If we sub in our expression for n of t from earlier, we arrive at the following expression for the activity of a single isotope decaying away. A of t is lambda n naught times e to the negative lambda t. So for a sample of an unstable isotope, activity is directly proportional to the sample's population. This makes sense conceptually, because we would expect a larger collection of radioactive atoms to be more radioactive. Activity also grows with the decay constant, which makes sense as a larger decay constant means that a collection of isotopes will decay away at a higher rate. Before we move on from talking about activity, I want to quickly introduce a couple of units that we use to describe it. As we've established, activity at its core is just a quantity which describes a rate of decay, with dimensionality of inverse time. Because the magnitudes of activities we encounter in the wild can span many orders of magnitude, there are 2 commonly used units that we put activity in terms of. These units are the becquerel and the curie. The becquerel is the most basic unit of activity, named for French physicist Antoine-Henri Becquerel, who discovered radioactivity in conjunction with the legendary Polish physicist and chemist Marie Curie. It's equal to 1 decay per second, simple as that. So a sample of material with an activity of 1000 becquerels will have within it 1000 decays occurring every second. In the grand scheme of things, a becquerel is an extremely small unit to have much use in the context of any real-world problems. The minuscule amount of americium-241 in household smoke detectors has an activity of about 37,000 becquerels. So we frequently discuss activities in terms of the unit's SI multiples: kilobecquerels, megabecquerels, gigabecquerels, and so on. We describe larger activities in terms of curies, named of course after Marie Curie. 1 curie is equal to 3.7 times 10 to the 10 becquerels, or 37 billion decays per second. This is roughly the activity of 1 gram of radium. Now modern measurements put the actual specific activity of radium-226 closer to 3.66 times 10 to the 10 becquerels per gram, but by the time this measurement was conducted, the unit had already been defined. One last topic to cover before we solve decay equations is branching ratios. Many isotopes are capable of undergoing more than one mode of decay. These different decay modes can and will occur at different rates, so they have different decay constants. Just as an example, any isotope that can undergo beta plus decay can also decay through electron capture. And in heavier isotopes, electron capture often occurs at a greater rate than beta plus decay. The overall decay constant can be calculated as the sum of the individual decay constants which correspond to each unique decay mode. If we divide both sides of this equation by the overall decay constant, we get the following expression. Each of these terms on the right-hand side is the branching ratio for a different mode of decay, which we represent with the letter F. A branching ratio is just the probability that a decay will be of a specific type, and as we can see, the branching ratios have to sum to 1. Now, we can finally start to solve some decay equations. Because we're primarily interested in seeing how populations of radionuclides change over time, and because the rate at which these populations change is related to the size of the populations themselves, we're going to need to solve some differential equations. In this video, we won't need to use anything more advanced than integrating factors, so don't be too worried if you aren't super familiar with the techniques used in this branch of mathematics. The simplest example we can come up with here is a case where one isotope decays into another. We can call the first isotope X sub 1 and the second isotope X sub 2, and X sub 1 has a decay constant of lambda sub 1. We start by setting up the differential equations that describe the population of these two isotopes. For x1, dn1 dt equals negative lambda 1 n1 of t. So we can do a little rearranging and then solve this first order linear ordinary differential equation with the help of an integrating factor, which in this case is equal to e to the lambda 1t. And then we do a little calculus and solve for n1 of t. Our final expression is n1 of t is n1 at t equals 0 times e to the negative lambda 1t, classic exponential decay. For x2, we can also set up a differential equation. The change in the population of x2 will have two components. The population of x2 will grow as x1 decays away and shrink as x2 decays away. So dn2 dt will equal lambda 1 n1 of t minus lambda 2 n2 of t. Now, in this example, x2 is a stable isotope, so it actually won't undergo decay, so lambda 2 equals 0. Now, we've already solved for m1 of t, so we substitute that in, and then we just integrate both sides with respect to time from 0 to t to get our final result. After a little bit of rearranging, n2 of t equals n2 at t equals 0 plus n1 at t equals 0 times the quantity 1 minus e to the negative lambda 1t. The first term, n2 of t equals 0, is just the initial population of x2. The second term represents the new x2 atoms that result from the decay of x1. Let's plot these populations and mess around with the parameters a bit to get some intuition here. On the x-axis will be time, and the right axis will be the number of each isotope. Keep in mind that the equations here are continuous functions, but decays occur discretely. So for small numbers of isotopes, like say 10, these curves won't be accurate, and they should really look like a staircase. But for nearly all applications in nuclear engineering, the number of particles is so high that a continuous function is acceptable. So you can imagine the y-axis being in terms of something like moles. The parameters available for us to perturb are x1's decay constant and the initial populations of the two isotopes. If we increase the decay constant, x1 decays away faster and x2 builds up quicker in turn. If we increase the initial amount of x1, we can see that the final amount of x2 that we end up with grows as well. Finally, if we increase the initial amount of x2, there's no impact on x1. Another interesting case we can solve for is the case where an unstable isotope is being produced by some outside process. This could be something like the production of radioactive isotopes within a cyclotron. The differential equation which describes this scenario is as follows. The change in the population of x1 is equal to negative lambda 1 n1 of t plus q of t. So the first term on the right-hand side of the equation describes the decay of x1, and q of t is some arbitrary function which describes the production of x1 over time. Now if we get the production term by itself on the right-hand side of the equation, we end up with something very similar to the decay equation we solved just a minute ago. Our integrating factor is the same, e to the lambda 1t, and if we multiply it into both sides and factor the left-hand side, we get the following relationship. From here, it's just a matter of integrating both sides from 0 to t, and then we solve for m1 of t. So this is our general formula, which describes the population of an unstable isotope, which is also being produced by some outside process, and it's valid for any arbitrary production function. We still have an integral on the right-hand side, so let's solve for the case where we're producing the isotope at a constant rate. This is a pretty trivial integral to solve, and after a little bit of rearranging, we find that n1 of t is equal to n1 of 0 times e to the negative lambda 1t plus q over lambda 1 times the quantity 1 minus e to the negative lambda 1t. Notice that if the rate of production was equal to 0, we would have the expression for an isotope decaying in isolation, as expected. So the first term represents the initial isotope's population decaying away over time, and the second term represents the portion of x1's population that's attributable to the outside production as it builds up and decays away. Now just like the last example, we'll plot x1's population and mess around with some of the parameters to see how things shake out. Initially, we'll set q to 0, and you see that we get our familiar exponential decay curve. And adjusting lambda changes the rate of decay, just as expected, and adjusting n1 of 0 changes the initial population like it did before. But when we change q to be non-zero, we get some interesting behavior. Now that q is positive and we're producing the isotope, we can see that the population doesn't approach 0 as time goes on. It approaches some other value. If we set t to infinity in the governing equation, we can derive that this value is equal to q over lambda 1. When the population of x1 is equal to this, the rate of x1's decay will perfectly match the rate at which it's being produced. So we can say that as t goes to infinity, X1's activity will approach Q. This state, where the amount of an isotope remains constant because its production and decay rates are equal to one another, is called secular equilibrium. The population will always approach the production rate over the decay constant, regardless of what values we set our parameters to. So the magnitude of the initial population just determines whether or not we approach Q over lambda from above or below. And the equilibrium population of our isotope is set by the magnitudes of its production rate and decay constant. Now that we've solved for some of these simple decay equations, let's move on and try and get some solutions to some more complicated setups. When radioactive isotopes decay in the real world, there's often a great many steps that an unstable isotope will make its way through in its journey to become stable. And along the way, there are often several different pathways that can be taken with varying probabilities. If you watched my first video on nuclear decay, you may remember the decay chain that we walked through for thorium-232. There were 10 decays that it needed to undergo before it became lead-208, and that was just the most likely path that it could take. So the systems of differential equations which govern real-world decay can get pretty big, and that leads to a lot of complexity when we try and solve them with the techniques we've used so far. Just to give you a little taste of how bad things can get, I'll show you the equations that govern a two-step decay equation, where x1 decays into x2, which then decays into a stable x3. So the system of differential equations that governs this is as follows. The change in x1's population is negative lambda 1 m1 of t. The amount of x2 grows with the decay of x1 and decreases as x2 decays, so dn2 dt is lambda 1 m1 of t minus lambda 2 n2 of t, and the amount of x3 builds up with the decay of x2, so dn3 dt is lambda 2 times n2 of t. We already solved for the case of n1, it's just exponential decay. For n2 of t, the solution gets a little more involved, as unlike the two-step decay chain from earlier, x2 isn't stable here and it'll undergo decay with time. But we can still solve it with the help of an integrating factor, and after a little calculus and algebra, we get this slightly uglier expression. Feel free to pause the video here, by the way, if you want to step through the derivation yourself. The first term represents the original population of x2 that decays away with time, and the second term represents the population of x2 resulting from the decay of x1, which builds up and eventually decays away.
Now, while the differential equation for n3 of t looks nicer, solving it is actually even more tedious, so I won't talk through the math here, but it's just using another application of an integrating factor to get to a solution. And you can see that it's getting pretty messy here. But the first term is just the initial amount of x3, which is stable and doesn't decay away. The second term is the initial amount of x2 that decays into x3, and the final big term on the second line is the initial amount of x1, which decays into x2, and then x3.
If we plot the populations of the three isotopes, we see that x1 decays away, as expected. x2 has a more complicated behavior, as it'll build up in the system as x1 decays, but then it must itself decay into x3, which builds up as t goes to infinity. Changing the initial amount of x1 alters the total amount of isotopes in the system, which need to pass through all three states, so all three curves scale accordingly. Changing the initial amount of x2 has no bearing on n1 of t, but it does have downstream effects for the population of x3 as a function of time, and changing the initial amount of x3 just shifts its curve alone since it's stable. All three curves are sensitive to the value of lambda 1, since it controls the rate at which x1 decays into x2, and thus impacts the amount of x2 available to decay into x3 at all points in time. Changing lambda 2 doesn't impact n1 of t at all, but it does impact how quickly x2 decays into x3. Something interesting happens if x2 is much more unstable than x1, which is to say lambda 2 is much larger than lambda 1. Here, we basically have a situation where the instant an atom of x1 decays into x2, that x2 atom decays into x3. This means that we never really build up an appreciable population of x2 in the system. It decays away too quickly. And the result is that the curves for m1 of t and n3 of t effectively resemble those for the single-step decay chain that we solved for earlier. It's as if x2 isn't even there. In this case, if we instead plot the activities for x1 and x2 as a function of time, and remember that activity just means the rate of decay, we see that the activity for x2 quickly jumps up to that of x1 and follows it more or less exactly. This is a function of the fact that because the decay constant of x2 is much larger than that of x1, we basically get an x2 decay the instant we have an x1 decay. This state, where the activity of a daughter isotope matches the activity of its parent due to a difference in their decay constants, is called transient equilibrium. If lambda 2 is closer to lambda 1, the decays don't occur in lockstep, so a population of X2 can build up, resulting in a mismatch of their activities. These equations we've been solving have a special name. They're Bateman equations. They take on this familiar form, where the value of each of the functions increases as its parent function shrinks and decreases proportional to its own value. And for the special case where all of the initial populations of all of the isotopes except x1 are 0, we actually can get a general solution to the Bateman equations in this unsightly form. In practice though, it's really only worth going through the process of getting an analytical solution to these equations for these cases that we've analyzed today. Once things even get a little bit more complicated than this, it's worth using some other mathematical techniques to get our solutions. I'll close things out for this video by talking through the matrix exponential method, which we can use to solve more complicated decay chains with the help of a computer. We've just seen how nasty things can get for a simple 2-step decay chain, so you can imagine how bad things can get if we added more steps, or if we allowed some isotopes to undergo different decay modes, resulting in forks in our decay chains. Just solving for a simple 3-step decay chain takes a couple pages of calculus and algebra. The matrix exponential method works as follows. We start by writing out our Bateman equations for the decay chain we're interested in, and just to make things easy, we'll do this for our 2-step decay chain. So here's our Bateman equations. They look the same as before. And what we can do is write out all of the hidden terms here, where we'll explicitly add terms to our equations which mathematically link isotopes that actually have no bearing on each other. So for instance, the population of x1 is in no way dependent on the population of x3, since x3 is downstream of it in the decay chain. But we can still write a term that links x1 to x3, so long as the coefficient on n3 of t is 0. After writing out these expanded Bateman equations, it becomes pretty clear that we can write this system of differential equations in matrix form. Here, each row in the big matrix of coefficients corresponds to an equation for an individual isotope, and each column sums to 0 since the total population of isotopes doesn't change. We can write this a little more succinctly as follows. Little n of t will represent the vector of isotope populations, so the left-hand side is just dn dt. The matrix of decay constants we'll write as big lambda, and the final vector is just little n of t. The solution to this differential equation of matrices will be as follows, where little n of t will be the matrix exponential of big lambda times t times the vector of the initial isotope populations. Now, the matrix exponential is something that we can solve with a computer through the following process. Recall that we can take the Taylor expansion of e to the x about x equals 0 as follows. It's equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. Well, a similar expansion can be written for e to the lambda t as follows. It's the identity matrix with the same dimensions as lambda, plus lambda times t, plus 1 over 2 factorial times lambda squared, t squared, plus 1 over 3 factorial times lambda cubed, t cubed, and so on. With the identity matrix just being a square matrix with 1s on the diagonal and 0s in all other positions. So this expansion would be a nightmare to calculate by hand to any degree of accuracy, even for a trivial problem like this little 2-step decay chain. But computers are perfectly slated for this task. The solution to e to the lambda t will give us a matrix of coefficients that, when multiplied with the vector of initial isotope populations, will give us solutions for the populations of our isotopes in the decay chain as a function of time. So let's do an example that's a little bit more complicated. This is actually a problem that I had to solve in my first nuclear engineering course that I took as an undergrad. Here's our decay chain. There's 8 isotopes in total. x1 decays into x2 85% of the time, and into x3 15% of the time. x2 decays into the stable x4 40% of the time, and into x5 60% of the time. x3 decays into x5, x5 decays into x6 and x7 with branching ratios of 0.25 and 0.75 respectively. x6 decays into x7, and x7 decays into the stable x8. The decay constants we'll use here are as follows. Note that for x4 and x8 they're equal to 0 since they're stable and they don't decay into anything else. And then here are the differential equations which describe this decay scheme. Now you can imagine that solving these analytically would be a pretty ridiculous thing to do, so let's put this system of equations in matrix form. To solve this, all it will take is a few lines of code. Here's all you need in Python to create a function to solve any decay equation in matrix form at some point in time. And after running this code, we can plot the activities of our different isotopes as a function of time. For our initial condition, I picked the case where we only have isotope x1, and its population was set so that the initial activity is 1 curie. Now we'll create this plot on a log-log scale, since the numbers we're working with here get pretty big. We see that x1 decays away with time. This leads to a buildup of x2, which also decays away. After building up initially, we actually get a period of relative secular equilibrium with x3, as its production roughly equals its decay up until around 10 to the 5 seconds. x4 is stable, so it just builds up over time. x5 has 2 production modes, so we get this sort of double bump shape in its plot, as x2 and x3 decay into it at different rates. x6 and x7 build up as x5 decays, and then they too vanish with time. And then finally x8, which is stable, builds up in the system. If we instead plot the activities, we get a similar looking plot, but all of the curves of course go to 0 with time. Towards the end of the sample's life though, we can see that x6 and x7 are effectively in transient equilibrium with one another and decay at almost the same rate, as the decay constant for x7 is much larger than that of x6. And that's all I've got for the math behind radioactive decay. Thanks for watching. I hope you feel more comfortable with the concepts of activity, branching ratios, half-lives, and the mathematical techniques we use to solve decay chains. I haven't decided what topic to make the next video on, but I hope to see you there. Thanks.